Wave-particle duality, the dual nature of light and matter. Have you ever wondered how light behaves? Is it a wave that spreads across space, or is it a particle that travels in discrete packets? This question has puzzled scientists for centuries. Today, we're going to dive into one of the most fascinating concepts in quantum physics, wave-particle duality. What is wave-particle duality? Wave-particle duality is the concept that every particle or quantum entity, such as photons, particles of light, or even electrons, exhibits both wave-like and particle-like properties. This means that light can behave like a wave in some situations and like a particle in others. This dual nature is one of the foundational principles of quantum mechanics and has profound implications for our understanding of the universe. The double-slit experiment. Let's begin with a famous experiment that demonstrates this phenomenon, the double-slit experiment. When light passes through two narrow slits onto a screen, it creates an interference pattern, a hallmark of wave behavior. The bright and dark fringes on the screen result from constructive and destructive interference, which is characteristic of waves. However, when we try to observe which slit the light passes through, the interference pattern disappears, and we see two distinct bands, as if light were behaving like particles. This indicates that the very act of measurement collapses the wave-like behavior into particle-like behavior. A similar result occurs with electrons. When electrons are fired one at a time through the slits, they also produce an interference pattern, but only if no one is observing them. If we observe their path, they behave like tiny particles, creating two bands on the screen. This experiment encapsulates the mystery of wave-particle duality and highlights the role of observation in quantum mechanics. Light as particles, photons. In the early 20th century, Albert Einstein explained the photoelectric effect, where light ejects electrons from a metal surface. He proposed that light is made up of discrete packets of energy called photons. Each photon carries energy proportional to its frequency, given by the equation E equals hf, where h is Planck's constant, and f is the frequency of light. This particle-like property of light provided crucial evidence for wave-particle duality. It also laid the groundwork for quantum theory, as it showed that energy is quantized, existing in discrete units rather than as a continuous flow. Matter waves. Interestingly, wave-particle duality doesn't just apply to light. Louis de Broglie extended this concept to matter, suggesting that particles like electrons also have wave-like properties. He proposed that any particle with momentum p has an associated wavelength, given by the de Broglie equation. Lambda equals frac hp, where lambda is the wavelength, h is Planck's constant, and p is the momentum of the particle. This was experimentally confirmed when electrons produced an interference pattern in a double-slit experiment, just like light. These matter waves form the basis for quantum mechanics, describing phenomena at atomic and subatomic scales. Why does wave-particle duality matter? Wave-particle duality is more than just a theoretical curiosity. It's a cornerstone of quantum mechanics and has profound implications for our understanding of the universe. For instance, quantum tunneling. This phenomenon, where particles pass through barriers that seem impenetrable in classical physics, and relies on their wave-like nature. Electron microscopy. The wave properties of electrons allow us to build microscopes with resolutions far beyond the limits of optical light. Quantum computing. Wave-particle duality is fundamental to the principles of quantum superposition and entanglement, which underpin quantum computing. Philosophical implications. Wave-particle duality challenges our classical intuition about the nature of reality. At the quantum level, particles and waves are not distinct entities, but rather different manifestations of the same underlying reality. This duality blurs the boundaries between concepts that were once considered separate and forces us to rethink our understanding of the physical world. It also raises profound questions about the role of the observer in shaping reality. The broader scientific impact. Wave-particle duality is not limited to light and electrons. It applies to all particles, from protons and neutrons to entire atoms and even some molecules. As experimental techniques advance, scientists have observed wave-like behavior in increasingly larger systems, further blurring the line between quantum and classical physics. Additionally, the concept has inspired advancements in quantum field theory, where particles are seen as excitations in underlying fields. This theoretical framework unifies the wave and particle descriptions and provides a deeper understanding of the universe's fundamental structure. Conclusion: wave-particle duality is a fascinating and counterintuitive concept that reveals the mysterious nature of quantum physics. It teaches us that light and matter are not limited to behaving as purely waves or purely particles, but can exist in a dual state, depending on how we observe them. This duality is not just a feature of the quantum world. It's a reminder of the richness and complexity of the universe we live in. If you've enjoyed this exploration of wave-particle duality, make sure to like, subscribe, and share your thoughts in the comments below. Let's continue unraveling the mysteries of quantum physics together.